Okay? So when we look at substitution reactions, we had issues with stereocenters. We get R versus S. When we look at elimination reactions, we have a very similar situation, and that comes into play with this E versus Z, which is effectively the same thing as our trans versus cis. Okay, so you will need to remember how to identify these. Instead of looking around a ring, which we did in chapter, anybody remember? Oh, 4. Okay, there we go. Chapter 4. We're now looking at it around a double bond. So the double bond is going to be our center point and deciding where our groups are located. Okay, so we did talk about this on Monday, so we'll just kind of jump into it. If we were going to take a look at that ring structure, we might attempt to go through and assign E versus Z around the double bond. So to start, what we want to do is cut the bond in half, perpendicular to its axis. So we're looking through this situation, right through the middle. We would then look at the groups attached on either end and star them. I should probably draw that hydrogen more like a hydrogen. And star them according to their priorities. The priorities are determined based on your Kahn-Ingold pre-log priorities, so based on atomic mass. So if we go through and look at the bottom half, we're looking at carbon versus hydrogen. Which one has a higher priority? The carbon, so we can star that. We can go to our top half. Same situation, carbon versus hydrogen. Carbon gets starred. We then go through and cut our double bond in half through the axis. And we look to see where our stars are located. Are they on the same side or opposite sides? Same side. So we could call this cis, but that really only refers to those two carbons. Those carbons on that ring are cis to each other. Okay? If we want to go through and name our compound, we wouldn't use cis. We would use that E versus Z nomenclature. So in this case, we would say that this is the Z ring structure. Okay? Questions about how we came to that determination? So we're going to add one little wrinkle to this. Look at the very bottom. What does it say? Any ring less than 7 carbons cannot be trans. Okay? If we have a trans configuration, there's no way that we can actually get the carbon chain to loop back around and connect if we have less than 7 carbons in this ring structure. Okay? So while we may have identified this one as Z or cis, that's true, it is, but could it ever possibly be trans or E? No. Well, if it can't do that, then we aren't going to bother to name it according to that EZ cis trans nomenclature. So with this ring structure, we wouldn't even have to name it as our Z conformation because we can't possibly get the E. Okay? So remember that when you're talking about rings. You will not refer to them according to the cis-trans or EZ conformations with double bonds if that double bond is incorporated into that ring and we have less than 7 carbons. Okay? Questions about that? All right, let's do one more example. I'll actually give you time to kind of work on this last one. If you got questions, raise your hand, and I will come around and talk to you about helping you figuring out how to go through and put that E. Bromine has a higher molecular weight, or sorry, atomic mass, so we can star that bromine. Shift to the other half, we're looking at carbon versus hydrogen. Our carbon has a higher atomic mass. Once we've gone through and done our stars, we can then go through, cut it in half parallel. Our stars are located on the same side of that line. So this structure would get the Z or cis moniker. If we're going to go through and actually name the compound, we won't use cis because that's our informal naming system. We'll use Z. Okay? So now this is where it's going to get a little bit dicier in trying to name this structure. Let me clean all of that up. We would start off our name with the Z, which is in reference to cis of what? The double bond. So we need to specify where that double bond is located within the main structure if we're going to go through and put our name together. Okay, so if we're going to name this, we'd go through, first identify our longest carbon chain, which is 5 carbons. So we've got a pentane. Where's our double bond start?
Say 3 and 4.
Okay, we've got between 2 and 3 or 3 and 4. Which one do we use?
3 and 4.
Why do we use 3 and 4? Which group takes priority, alkenes or alkyl halides? Alkenes take priority. So we're looking at a 2-3 double bond. So if we're going to reference that Z needs to reference exactly where that double bond first appears, which is at position 2. So it's going to be 2Z. Okay, whoops, and I messed up the overall ending. Because this is a 5-membered structure, we've got a pent name coming. Oh, pent. No wonder it looked weird. We have a pent. Yeah, it's a fish. Fritz. It's an alkane, or is it an alkene? It's an ene, so we have to change the ending on it. It becomes a pentene. Where did the double bond show up? Position 2, so we can call this a 2-pentene. Do we have any substituents on this structure? Yeah.
3 and 4.
We've got bromos at position 3 and 4. So we could go through and call this our 2Z, whoops, specify our numbers, 3, 4, dibromo 2-pentene. Is there anything wrong with that name?
Is there a hyphen between bromo and 2?
Yeah, you'll need a hyphen there. Way to point out my mistakes. Do we have a stereo center?
Oh, no.
Yeah, so we'd have to determine if it was RS and also include that in our name. Okay. So in this case, we really only have 2 functional groups, but you've got a cis-trans issue and you have an RS issue that would all have to be pumped into this name. Okay. Where all of that information goes, typically it's thrown in at the front. We'd go with a 2Z. What is that, 4? Is it R?
I'd say it's on. I say
1, 2, 3, yeah. It'll be 4R. So we'd go 2Z, 4R, 3, 4, dibromo, 2-pentene.
2Z, 4.
4R for that stereo center. Okay. This is kind of an illusion question, or a foreshadowing question. I'm not expecting you to be able to do this nomenclature yet. What I expect right now is recognizing your Z versus E and realizing that we generate different products out of that. Okay? So, why evaluate this? If we look at our unimolecular elimination with a slightly more complicated question, okay, in this case I actually gave you a little bit of hints along with this. So we're running with a secondary substrate, saying we're doing the elimination. So I've given you heat or a delta symbol as both characteristics of our elimination. It doesn't guarantee it, but it does kind of raise a red flag saying we might be doing an elimination. We form the carbocation first, and then because I'm telling you it's an elimination, you should be able to predict the possible products out of this. Okay, so again, I'll give you the freedom to attempt on this. And I'm going to kind of talk over you while you think about it, just because I'm mean. The other name that typically comes with your eliminations, we don't refer to them as just eliminations. You'll also hear reference to a beta elimination. That beta elimination is in reference to the idea that if we look where our leaving group is located, that is the alpha position. If we move one atom away, we have the beta position. Why might we refer to it as a beta elimination?
Because the H from the beta position.
The H from your beta position is removed from the structure to go through and form your final product. Okay? So what products do you get out of this? You don't have to name it.
Well, I didn't know it was going to take a long
That's a bad question, I guess.
You get that with the double bond.
Okay.
Yeah.
We're going to have to bring in the double bond. So what's happening in that case, if we look at another drawing, we've got our carbocation represented by that p orbital, and then we've got the beta hydrogen highlighted in red. So if we take a look at the structure on the left, what will end up happening is our base, or our heat, will cause the electrons in that bond to go in to form the pi bond. So if we draw that out, what will end up happening is I will have my wedge still coming forward there, my wedge over here, my bond, and then my dashes back to the hydrogen, right? Everyone agree with that drawing? Oh, and a pi bond.
No, that's wrong.
Okay, why is it wrong?
They're the wrong place.
What's in the wrong planes? All we're trying to show is that that previous structure, that these two are tied to each other, directly related. Okay. Dash pointing down, good question. Where should this dash end up? What happened to the hybridization of the carbon? Became sp2. What's the orientation of the bonds around an sp2 atom? What's that shape? Trigonal, planar. Which means where are those bonds? All in the exact same plane. So when we remove that hydrogen up top, what we've done is remove that electron density. What was forcing those groups down, there's no more electron density. So what do? They pop upwards into that plane. Okay, so we don't have any hydrogens necessarily down in this case. So all we're trying to show is that we've got those wedges coming at us. Because we're forming that pi bond, once that pi bond is formed, it can't rotate, so we're locked in this conformation. Do you guys see where that structures or how those structures are tied? Because if you don't see that, it's going to make this a lot more difficult. Is that a yes? Okay, I heard 2 or 3 in the crowd. That sounds good. With a trigonal planar atom, all those bonds are in the exact same plane. Okay, which means, is it necessary to show the wedges and dashes? No. So what we can do is take this structure that is currently aimed directly out of the board and just kind of pull it out and rotate it so it's now flat in the plane. When we go through and do that, our structure is going to look like this. Agreed? Okay. Seeing some heads shaking. What happens to our methyl groups? Where are those methyl groups located? They're located coming directly out of the board at you. If I take the structure out, so let's double prong it. If I take the structure out and I rotate it downwards, where are those methyl groups? Both aimed directly down. In my drawing, are they both aimed directly down? Yeah. Okay. So all we're trying to show is how we can convert from one of those drawings to another to yet another view to get that overall image. Everybody with me on that drawing? Okay, so let's try the next one. If we take a look at that beta position, how many hydrogens are located on it? We have 2 hydrogens, which means we have the potential for both of those hydrogens being removed. Okay? So what we can go through and do is look at a slightly different orientation. What we'll do is rotate about the sigma bond. Okay, we're allowed to rotate about this bond. Why? It's sigma. As we do that rotation, the overlap never changes. So that is an absolutely valid thing to do. So what I've gone through and done in this case, because I actually didn't use the blue hydrogen, we took that red hydrogen, and I've now rotated the structure. Let's make sure I did that. Yeah, I took that red hydrogen, and I've now rotated it down so it's now aimed out at you. Okay, that's what's happening in this new drawing. Everybody see that rotation? Okay. In that new rotation, I still have the hydrogen and its electrons in the same plane as the pi system, or as our p orbital, which means I can shuttle electrons across, and what I can do instead is show the electrons doing this. What's the end result if that's the case? Well, our wedges are still coming out at us. What's the wedge on the leftmost atom? A hydrogen. On our rightmost, our carbon or our methyl. We also have the dashes. All right, what happens if we now take this weird wedge dash structure and take it out of the plane and rotate it down so that we can put all those atoms into the same plane? Do that one awfully large. Exact same mechanism. Do I generate the same product? No. Interesting. When we go through and run the elimination reaction, we have the potential for both of these products showing up in our answer. What is the relationship between these two structures? They are cis and trans isomers, so you could refer to that. Or we could go back to structural, not structural. Cis and trans isomers is our classification on these. Okay, because we haven't changed the location of any atoms, so we don't have a structural isomer. Okay? So if you're asked to provide the product, well, what's your answer? We could go with both, but then that begs the next question. Are both of these equal in energy?
No.
Well, if they're not equal in energy, are they both likely to be there in the exact same concentrations? No. Which means not only do we have to evaluate that both products are formed, but which one is formed predominantly. Right? To determine that, we can go through and look at individual transition states and evaluate those. We'd be looking at energetics. Ultimately, what we would be concerned about is what's happening in each of those drawings, but from the appropriate viewpoint. That appropriate viewpoint would have to be, particularly if we're looking at energy, which one of our structural drawings allows us to see energies? Newman projections. We'd have to redraw that structure into a Newman projection, and what you'll end up seeing is that in the structure on the left, we end up bringing our two methyl groups very close to each other in a pseudo-Gauss type orientation. What happens in the structure on our right? They go into an anti-conformation. Which conformation is lower in energy? Anti. Which double bond or which product is going to be the favored product? The one to the right. How do we refer to the one on the right? It's trans or E. We end up generating, very typically in an elimination reaction, the trans product. And that's because that cis product has a steric interaction that prevents that elimination from occurring to any large extent. So while both products are present, we would go through and typically specify that the one on our right, no, I didn't add a hydrogen. It's just too close to the previous drawing. The one on our right with that trans orientation is the major product. Okay. What if the question doesn't...
Saw that from the last structure there? Isn't that the same thing?
Isn't that the same thing as what?
I mean, that's the opposite, so you know that that's trans, that's cis.
We know it's trans and this is cis, but the question then becomes why? Which one is the favored product?
The one that's going to be...
The one that's going to be trans, and this is where we run into kind of hand-wavy arguments. We can go through the argument that we're putting our two largest groups away from each other in our final product, okay, which is a valid description, but that assumes we're looking at the product. Do we have the product before we make the product? No, so we can't use that as an answer. Okay, so what you'd be doing is explaining, I have this, it's A because it's got the shape of A. Well, you're using the answer to define your answer. You can't do that. That's why we would more strictly go back and look at the transition state for those reactions and say, when we look at the Newman projection, we have to have that proper alignment. All right, does everybody understand what she asked? All right. What she's saying is, can't we just look at the product and say that we should get trans? All right, why would we expect trans to be lower in energy? We took our two groups, our largest groups and we put them as far away from each other as possible. That should make them lower in energy. Okay. That explanation assumes you have the product. If you don't have the product yet, you can't use the product as your answer. Very circular logic. So what you would have to go through and do is look at your transition state with your carbocations and look at the Newman projections to get to an official answer. Okay, so it's a question of how do you describe or define your answer. Kind of makes sense? Yes?
And that's where you would describe it as an anti-conformation.
An anti-conformation in the transition state.
Okay.
Okay? So we end up with both of those possible products. What we would expect is that the one on the right would be our major product. That's an eraser. So we could specify major. And apparently major spelled with 2 A's. That now looks like a U. So let's just move to the next thing. So the relationship between our products is that we have this cis-trans relationship. We cannot convert easily between them. Why can we not convert easily between them? We won't rotate about the pi bond because we break the p orbital overlap within the pi bond that actually prevents or reduces or increases its energy. Sorry. Okay. What we can refer to in this case is what's known as our regiochemistry. We favor the trans product. So regiochemistry is just where did those bonds actually end up forming? How was that our relative alignment? So it's related to our stereochemistry, but not quite the same thing. Okay, so we'd expect the trans because we got our biggest groups far away from each other. Okay, was there another product? We said beta elimination, so we looked to the beta position, which was 1 carbon away. So if we go back and look at our structure, there's our alpha, and I drew beta up there. Is there another beta?
Yes.
Did anybody draw that product?
Yeah.
Oh, good job. Okay.
I didn't draw the 2 from the first one, though.
Okay, so less of a good job. We have 2 beta positions with beta hydrogens. Both of those positions can potentially react in this elimination. Depending on the conditions we're in, we might see one over the other. If we go through and push that, we end up with that 3rd product. Okay, this is just getting obnoxious. Okay, we've got an elimination reaction, a single type of mechanism with 3 possible products. Okay, within the first 2, we said, okay, we expect the trans, but what about that last one? Would we expect that one to form?
No.
Why not as much?
Well, you eliminated one of the other hydrogens, right?
We eliminated one of the other hydrogens. Do we have a cis-trans issue? It's only got 1 R group, so there's no cis interaction to actually make this one less stable. Okay, so why do we not form this one?
Is it energy levels? Newman projection?
Well, isn't it still dealing with the alpha position instead of the beta position?
It's still a beta position. So our alpha position is where the leaving group left.
Yeah.
So there's our alpha. Our beta is 1 carbon away. There's the first one we looked at.
Right.
There's the second one.
Right.
So we're still looking at a beta elimination in both cases. What we did was removed a hydrogen from that beta carbon
Oh.
to make our double bond, yeah, on the far right. Okay. We're looking at a primary carbon as well in this case, but if we even shifted to that logic, where should the primary anion be more, or which anion should be more stable, a secondary or a primary? Anion, the negative charge, should be more stable on the primary, which would suggest that this 3rd product would be more stable. Okay, because we generate our negative charge on that primary carbon. Okay. This one gets, and we still have the cation in the exact same position. That doesn't change between either of these products. Okay. This is where we can go into what I would recommend even more hand-waving for an argument, okay, is looking at the difference of these products. And the analogy that I like to go through is looking at the energy of stabilization through the extra carbons. If we look at that pi bond, that is what's the most reactive thing in each of these structures. Okay? So what we would do is evaluate its dynamics. The hand-wavy argument that I like to use, because it works very well for this, is which of those pi bonds would we expect to be more difficult to react? If it's more difficult to react, what does that do to its stability? Makes it more stable, which does what to its energy? Lower energy, which means faster reaction. It's the most likely product to come out of this. So if I can find the one that's the most difficult to react, that's going to be my product. Okay? So let's compare now, because we already looked at our cis-trans analogy. So hopefully everybody's confident with our trans being more stable than our cis. Let's go through and compare those last two products. If I'm going to take a look at that pi bond, how is it going to react? What makes the pi bond reactive? Electrons, which means it's going to act as a nucleophile. Those electrons must leave the structure. So I'm going to look at all relatively four directions in which those electrons come out. The electrons come out this direction. What do they encounter? What's the atom right there?
Space.
Hydrogen. How many electrons does hydrogen have? One. So there's a little bit of electron repulsion when it comes out that direction, but I mean, unless there's no bond there, we're not going to have anything, or we're going to have something. What happens if it goes out this direction? Carbon. What's the difference between our carbon and our hydrogen? More electrons. So what we've done is, with that carbon position, we've blocked the reactivity of our pi bond. It can't react in that direction. So when we take a look at our trans product, we really only have two directions that it can potentially react, going by those hydrogens. What happens when we look at the other product? Comes out and sees hydrogen. I'll draw the hydrogens in a second. It has three locations that it could potentially come out. Which one's more reactive? The one with three possible reaction sites or two possible reaction sites? Three. Which means which one's higher in energy? The one with more reaction sites. Which means what about which means our favored product is top or bottom? The top one.
But when you're drawing the arrows of which directions that pi bond should come out, couldn't it come out down to the right?
So this is definitely a hand-wavy argument, because officially where our electrons are located is above and below the plane. We aren't really going by any of those atoms.
Okay.
Right? So where the argument gets a lot stricter is looking at our Hammond postulate within our transition states and the formation of those. And it's also going to be addressed by the heat of hydrogenation, right, which is absolutely what I meant to include on this and didn't. What's happening with our heat of hydrogenation? And actually, I'm just going to make it as a new slide. Okay, our heat of hydrogenation is the energy involved in adding hydrogens. So it's a fancy word of react our structure with H2. So add hydrogen to our structure. So if we took a look at our standard case in all of those situations, we just have a standard butane, okay, fully hydrogenated. What happens if we have a pi bond? Should it be higher or lower in energy than that? Higher, because? More likely to react because the pi bond has p orbitals. Those pi electrons are more reactive. So if we took a look at putting in our pi bond, it definitely has to be a higher energy. Okay. If we look at the heat of hydrogenation for our trans system, let's say it's arbitrarily there, the heat of hydrogenation is the energy released to go from our alkene to our alkane. That's our heat of hydrogenation. So let's give that a number. Let's give that, 42. 42 is a good number. What happens if we take a look at our other product? Turns out the heat of hydrogenation for that other product ends up coming in at 50. Well, if the hydrogenation energy is more, what does that mean about the energy of that alkene? It has to be higher. If it's higher in energy, is it going to be as likely to form? No. Okay? So our heat of hydrogenations are used as a way to measure stability of the structure. The lower our heat of hydrogenation, what does that mean about the stability? The more stable. Okay? The higher our heat of hydrogenation, the more unstable. Okay? So we can use other experiments to go through and evaluate the relative energies of each of these things and take that back into our explanation. Yes?
One question, pretty unrelated, but so since the carbon on the bottom, since it's like a saturated carbon chain,
Yes?
is that why like saturated carbohydrates are bad for your body because it's harder to break apart?
No, that gets a lot more complicated than I would address here. That would, you in theory see that show up in a biochemistry class, or maybe they might talk about it in your standard biology classes. You're looking at all sorts of different reasonings behind that. Yes?
The final cis or trans product, is that an all or N?
Is that what?
An all or N? We can have both.
There is
Just
no
one.
R and N. I don't know what you're talking about with R and N.
These products, okay, we have.
When we look at our cis and trans products, how do we refer to them?
No, my question is, can we have both at the same time, or we just have either?
Oh, or and. You will typically get both. You will get one in a larger concentration. So that's why you would refer to it as a major product and a minor product.
Okay, we have both.
Yeah. Okay. First person to go through and note this. Oh, I didn't give his name right away, so let's avoid that. We can look at double bond. Leave it as a big surprise, right? Double bond substitution patterns. So in each of those double bonds listed across the top, we're referring to how many non-hydrogen things are attached to the atoms of the double bond. So in our tetrasubstituted case, what we're referring to are those four groups. That double bond is tetrasubstituted because it has four things that are not hydrogen attached to it. That ends up being a lot more stable than the trisubstituted. Why? What's its heat of hydrogenation going to be? Higher or lower than our trisubstituted?
Lower.
Lower. Okay? That means that that double bond is inherently more stable, and this is where you could go through whatever arguments you wanted to go through to describe why it's more stable. Okay? Trisubstituted, we've got those three groups. That last position is a hydrogen, so we ignore it. Disubstituted and monosubstituted, the same general idea. The last thing that we could address on that is under our disubstituted, we do have that cis-trans option. Our trans is a little bit more stable than our cis. Okay? So when we're looking at our products, what we're trying to generate in an elimination is the most stable double bond. Okay? Every time we do an elimination, regardless of what mechanism, we want to make the most stable double bond. Which means, when we look at substitution patterns, we want the most substituted double bond to be our product. Okay, so when you look at a structure and you see multiple beta positions, draw the elimination product for each of those positions, and then decide which of those eliminations results in the most substituted double bond. That is your major product. Okay? That observation was first noticed by, I believe he was a Russian, Zaitsev. So we have the Zaitsev's rule. Not a big fan of referring to it as the Zaitsev's rule because that just means you have to know another name. Really all it's saying is that the major product is the more substituted double bond. Okay? If you know that, that's good. If you know Zaitsev's name is attached to that, that's also pretty good. Okay? I won't give you too much of a hard time for that. I will probably forget it and confuse it with other people's names. Okay? So our Zaitsev comes back to elimination, make the most substituted double bond. Okay, if we notice really, really carefully at the bottom of this slide, though, notice in italics, small font. It says the fine print. We have an exception to Zaitsev's rule. Okay. The exceptions to Zaitsev's rule, because it happens fairly rarely, of course, gets another person's name. That other person was Hoffman, and what we can do is a Hoffman elimination. Very particular circumstances must be satisfied to push the Hoffman elimination. So the first option has to be an E2 elimination. Have we talked about E2 yet? No. So we don't have to worry about it quite yet. The next part of it is that we have to have a sterically hindered leaving group, which should be listed on there. What's going to be a sterically hindered leaving group? A tertiary alkyl halide will be a sterically hindered leaving group, because what we've got is a whole bunch of bulk around that leaving group. Okay? And a sterically hindered base. If both of those conditions are met, the Hoffman product dominates in the end result. Okay? Why would sterics play a role? If we looked back to the elimination that we just addressed, we'll call our Zaitsev blue and our Hoffman purple. Which of those hydrogens is more available? Said another way, which of those hydrogens is most external to the structure? The purple. So if I use a base that is very sterically hindered, it's going to react with the most accessible, readily available hydrogen, which is going to be the purple one. If I'm looking at a base that isn't sterically hindered, I'm now going to go through and form the most stable product, not the most readily available product. So we're looking at a thermodynamic versus a kinetic argument. Okay? Questions?
Why again was that
Whoops.
the purple one, the one most
Oh,
available?
double oops. Come back here.
Because it was next to the leaving group?
They're both next to the leaving group.
Right.
It's a primary carbon versus a secondary carbon. So that blue one, so we can do a steric argument with that blue one having 2 carbons near it, whereas our purple one only has 1 carbon. We could also go based off of numbers. The blue position has how many hydrogens? Just 2. Our purple has 3. So we have a larger amount, so it's almost a concentration dependence and a steric dependence.
So if in case of the purple hydrogen, which product do we have?
If you have the purple hydrogen, you're going to end up forming the less substituted double bond.
So that means the primary cap, right?
So our purple product, I don't know why that sounds funny, but it does, is that guy.
Oh, okay.
And our blue product, whoops, is that guy.
And the purple one, you call that the Hoffman.
The purple one is our Hoffman, so we can add that on here too. We've got Hoffman, and our blue one is our Zaitsev's, which is spelled like 6 different ways, by the way, so don't blame me on misspelling that one. You'll see it, man, it's never spelled with a Z at the end though.
Safe rule, also called the safe.
So you can see it with a Z, you can also see it written as Cephs. Okay. Silly Russians. No one can pronounce their names, they end up spelling it differently. Okay. Sorry if anybody's Russian. I guess I should have covered the mic on that one too. Heightened tensions and all, right? Zaitsev's rule. So let's go ahead and take a look at a reaction. If more than one elimination product is possible, then specify the most stable double, or sorry, that's not a question, that's a statement. Then the most stable double bond is formed. So if we start with the starting material shown here, what is going to be the product formed? So go through, attempt this. I'll give you a quick 15 seconds. Draw faster, Diego. Where's our alpha position? Where our carbocation is. Where are our beta positions? 1 carbon away. So we have 3 beta positions in this case, which means we end up with, I guess I can color code those. How many possible products? 3 possible products. Our blue product looks like and our purple and our orange. Which of those products is the major product? Our leftmost, or our blue one, because it is tetra-substituted as opposed to, this one's tetra-substituted. Our purple one has how many substituents? 2 di-substituted. And our last one has 3 substituents. Whoops. Which is, what is 3? Tri-substituted. Hi. It's a good favorite question for a lot of different reasons. The biggest one would be, right off the bat with a single question, we've got 3 multiple choice answers. All of them are valid. Okay. So we'd probably end up with one last one being a substitution reaction. Okay. So what you would need to go through and do is evaluate those reagents and which product does it push you to. In this case, the product we end up with as our major product is our tetra-substituted. In multiple choice exams, it is always what is the best answer. Not all of these are possible, but what is the best answer. In this case, our tetra-substituted is the best answer, regardless of how many other options are thrown out there. Yes, Diego.
How'd you get, guys, here with the hydrogen one on that pi bond.
Thank you. Which pi bond? Which
Well, the
hydrogen?
blue one. Why, for all of them, I understand, but like, why is it tetra, why is it di, why is it tri?
Okay. So we can go through with our reds. Take a look at that first one. Here's our double bond. We want to see the substituents on that, the non-hydrogen atoms attached to the double bond.
Okay.
Not a hydrogen. Not a hydrogen. Not a hydrogen. Not a hydrogen.
Cool. See ya. Thank you.
Okay. What's the most substituents you could put on a double bond? 4. Just checking. Okay. So you will always have 4 things attached, period. What we're concerned about is, are those 4 things that are attached not hydrogen? Okay. Other questions? Okay. Within our E1 summary, we've got everything set up on this. You'll notice that our rules for the E1 are very similar to our SN1. So we're looking for a stable carbocation to form. The leaving group still needs to be good. We're looking at a weak base because we don't care about the strength of the base because it's not dependent in our rate limiting step. The solvent is typically polar protic. Not that big of a deal when we're looking at our eliminations with our solvents because you will almost always see a polar protic solvent used for your eliminations, okay, regardless of the type of mechanism. Your regiochemistry, you will typically see mainly the trans product coming out of this, and that's just because that is the most stable orientation of those groups. Complications, we do have resonance and rearrangements. Why might we have resonance and rearrangements? Not because we have a pi bond. When do you look for resonance and rearrangements? Not a stereocenter either. Carbocation. As soon as you see a carbocation, there is resonance and rearrangements as a possibility. Every single time. Do not ignore it. If you draw a mechanism where a carbocation pops up, you should immediately be thinking, what can I shift to make this more stable? If you can't shift anything, then you can continue with the rest of your mechanism. Otherwise, you've got to go through that resonance or rearrangement situation and decide, is that a valid thing to do or not? Okay? So you get the exact same complication you get with the SN1, which brings up our very last issue with this. If you have an E1 elimination, it directly competes with the substitution mechanism. Okay? Because we don't look at the strength of a base or a nucleophile, so the only things that really separate at that point is your substrate and your leaving group. Well, if that's it, both of them have the exact same requirements for an elimination or an E1 elimination and an SN1. So if you're given conditions that you think is an SN1 elimination, what should you also provide as a product? The E1 elimination as well. You'll also have to pump out that elimination. How do you know that you don't have to specify that elimination product? When it says it's just substitution. Okay? Or when it says it's just elimination, you don't have to do the substitution. Okay? What?
If we have heat.
Heat is a red flag, but it doesn't guarantee it. Okay? Because heat speeds all reactions, it will speed your substitution reactions as well. Typically, to run an elimination reaction, we do add heat because we don't have anything to break that carbon-hydrogen bond, so we have to add enough energy in it to get that bond to break. There was another hand. Was it? I'll come back to you. What was that, Tim?
Did you just say that when we see an SN reaction, we need to, for all both products for SN1, E1, keep
Yes.
them together? Okay.
Keep them together.
All right.
So even in case of heat, we have to provide heat.
Even in the case of heat, you need to be aware that both products are possible. Okay? How often is that going to become an issue on a multiple choice test where you only have 4 answers? You're probably not going to see it all that often. Okay? As far as short answers go, absolutely, I'll push you on that. Okay? Because you need to prove that you understand what's going on with those reactions and their issues. But when it comes to the final exam, you won't see it pop up as much because they're limited with the amount of answers that they can put on there for a multiple choice test. Okay? Questions on the E1? So we'll move to the E2. What we're looking at in the E2 is very similar conditions as we saw for the SN2. We're now shifting to a biomolecular reaction. We're going to be breaking the carbon leaving group bond at the same time that we form the carbon-carbon pi bond. Okay? Because we're doing this all at the same time, we're now taking the exact same arrows that we used for the elimination, but now we put it all into a single step. Okay? So we've got our leaving group leaving, so the electrons in that bond go to the leaving group. The electrons in the bond between our beta carbon and hydrogen, those electrons move in to make the pi bond to force the leaving group to leave. Okay? Because one of our conditions with the E2 is that, or for our SN2 at least, that we couldn't form a carbocation. Okay? So something has to force the leaving group off. That's what our hydrogen electrons are going to do. In general, people are a bit dicey about just having electrons be removed from an atom, say like hydrogen. So we typically show something to help facilitate that bond breaking. With the E1, what helped facilitate that bond breaking? Heat. With the E2, as the name would suggest with that 2, a second species is introduced to help break that bond. That second species needs to be able to accept a hydrogen ion, which means that second species is also a base, and in particular a Bronsted base. So what we can go through and do is show the arrows. Come on. Did I not show the arrows? Oh, there they are. We can show the arrows where our base is going to share its electrons with that hydrogen. Okay? Because we're now introducing that base to force the leaving group to ultimately leave, what do we want as a condition for our base? It should be really, really strong so that it can pull that H plus off to facilitate that whole process going through. Okay? So here's a consistent pattern. For the SN2, what did we want in our nucleophile? Strong. For the E2, what do we want in our base? Strong. For an SN1, what did we want? Weak. For an E1, Weak. So if you look at the strength of your negative or your nucleophile or base, if it's strong, which mechanism are you pushing? The 2 type reactions. If we have a strong base or nucleophile, we're in that 2 column. Okay? If we have a weak nucleophile or base, we're running the 1 type. That can help us separate and simplify which mechanism we're evaluating. Okay? We're still looking at a backside attack, which makes this a little bit tricky. So in the SN2, we had a backside attack. In the E2, we still have a backside attack. We're trying to make a pi bond, which means we have to have p orbitals overlap to make that pi bond. Okay? Which means the electrons coming out of our hydrogen need to be in the same plane as the orbital that is now being vacated by our leaving group. If they're in a different plane, the electrons cannot come from the backside and cannot force that leaving group out. Right? So this viewpoint is a little bit odd to look at. It's very difficult to tell where those exact electrons are located, and that's because we haven't gone through and drawn in wedges or dashes. But I would argue even with the wedge dash situation, it's not very obvious. Where might be the easiest way to see that that hydrogen and that leaving group are on complete opposite sides of the structure? A Newman projection. So if we take our starting material and rotate it so that we can look at the Newman projection, that one looks okay. What I've gone through and done was took that front carbon, come on, highlight, took that front carbon and we pulled it out of the board and aimed it at you. In the process of doing that, we can now see the alignment of all those individual atoms and what's happening with those situations. I also went through and highlighted a couple different hydrogens. Okay? Because what we want to do is see which of those hydrogens is in the proper alignment to be able to chase the leaving group out. Okay? If we take a look at that red, well, let's skip the red hydrogen. Let's look at the blue hydrogen. I'm still seeing a lot of people, even with the E1, go through and look at that blue hydrogen. Okay? Based on the nomenclature system we just added in here, our alpha versus our beta, where is that hydrogen located? It's located at the alpha carbon. Do we do alpha elimination? No. Okay. Why do we not do alpha elimination? We have to make the pi bond. Those hydrogens, or those electrons have to chase the leaving group out. Okay. How can those electrons chase the leaving group out? At best, we could show those electrons going to that bond, but then we formed a pi bond between the leaving group and our carbon. That did the complete opposite. Okay. So when we're looking for our eliminations, you have to look for the beta position. The blue hydrogen does not work for an elimination. Okay. Where's our beta carbon? It's the circle atom in the back, and we have two hydrogens on that structure, a red one and a green one. Okay. For this elimination to work, the electrons in that bond must come directly behind the leaving group leaving. Where are the electrons in our green hydrogen? To the side at best. At worst, those are coming in at the exact same angle as our leaving group. We're going to get an electron-electron repulsion with our base coming in there trying to pull the electrons or pull that hydrogen off. That elimination does not work. What we're going to see that actually works is taking the electrons from our red hydrogen, and those will directly come in immediately behind our leaving group, and we can see that bond actually cleaving. What is the arrangement of our beta hydrogen to our leaving group?
Anti.
It is in the anti-conformation, which means to run an elimination or an E2 type mechanism, we must be in the anti-conformation. When we look at the initial problem that was drawn up there, can you tell that that hydrogen is anti to the leaving group? How about if we drew it like this? Can we tell if that hydrogen is anti to it? No. Why? We don't have any wedges and dashes to specify, that's our leaving group, sorry. Wedges and dashes to specify exactly where that orientation is. Okay, so you have to make sure that your drawing accurately reflects that elimination position. In the E2, we are concerned about stereochemistry because we have to get those atoms into the proper alignment. What you'll see within the sapling homework, whenever an E2 elimination pops up, is you'll see lots and lots of wedges and dashes because we'll need it on both of those reactive positions, our alpha carbon and our beta carbon. And what you may have to do is rotate about the sigma bond to get the hydrogen into that proper alignment. Once the hydrogen's in the proper alignment, we can do the elimination. What happens to the groups that are also attached?
They change position.
They're going to change positions as we rotate the hydrogen into its active position. Once the hydrogen's in the active position, can they change?
No.
No. Which means, how many products do we get?
One.
One. So it's a pretty significant difference from the E1 elimination. All right, one clarification on that. We get one elimination product per hydrogen being in the proper alignment. If we have multiple hydrogens, still have multiple products. Okay? So if we look at another version of it, another textbook had this kind of orientation, which might be a little bit cleaner to see. If we look at that top situation, our leaving group is that X, which is on the back atom, and our hydrogen is on the front. Our base comes in to pull off the hydrogen, and if we look at where it's located, that base with all of its I can't point to that. Our base with all of that electron density is now really far away from the leaving group with its electron density. So there isn't this steric repulsion, and we can actually see that elimination, or we don't get that steric repulsion, but then we can also see the electrons coming out of the hydrogen bond and forming that pi bond, okay, to get that proper overlap. What happens in the other circumstance? Okay. Our base comes in, and we see a repulsive force between our leaving group and the base, and we don't see that elimination happening quite as easily because the base will get chased away a large percentage of the time. Further, if we look at how the electrons are then trying to move, the electrons are also going to start to bump up against each other. We don't get that nice, clean backside attack that we would want out of a two-type mechanism. So in that, our bottom circumstance, that's just not a very favorable orientation. The odds of that reaction happening go to 0. Okay? The conclusion is that our E2 elimination can only occur when your leaving group and your hydrogen are in the anti-alignment. Okay? You'll notice it doesn't say directly anti, it says anti-periplanar. Still not quite sure exactly why they bring in that periplanar. There are certain circumstances where we can have a slight tweak to that angle and they're not perfectly anti to each other. So that's where it's almost planar. That almost planar situation does work. As far as you guys are concerned, what are you going to end up seeing? In the same plane, we're looking at that anti-alignment. So when you go through and do your homework problems, make sure your hydrogen and your leaving group are in the proper alignment, okay, which may not be obvious, and it may not even be drawn in the proper alignment within the homework. You may have to redraw the structure, forcing a rotation about that sigma bond to get you into the proper alignment so that you can do the elimination. Once you're in that proper alignment, that's now going to force the regiochemistry, be it cis or trans. Okay? So, let's go through and take a look at some E2 products. What are the products of your following elimination reactions? So we've got 2 bases. We've got hydroxide, and then we have T-butoxide. What's our big difference between these? Size, so we're looking at sterics. That bottom one is bulky, which means size is going to play a role in your answer for this problem. Okay? So I'll let you go through and attempt these. based on what we already talked about, you might be able to answer the bottom one a little bit easier than the top one. Because we're short on time and I want to get through more. Sorry. Anybody draw this product for the first one? Okay, why might we draw this product?
Most substitute.
It's the most substituted. What we said earlier, based on Zeissep's rule, we form the most substituted product. This is the product for an E1 elimination. It's not the product for the E2. Why is it not the product for the E2? You must have the leaving group and the hydrogen that's being removed in the anti-conformation, which means they are complete polar opposites of each other. If we look at this drawing, the bromine is aimed away. Where is the hydrogen aimed? Away. Are they polar opposites? No. So we cannot eliminate that hydrogen under the E2 mechanism. Which would leave two possible options. We'll actually draw the final or the correct one for this one. We'll end up with that elimination product for our E2. So we eliminate and form the less substituted product between those two. Why do we not form the completely less substituted product? Because there's another one. Because that one's less substituted. So when we look at our E2 elimination, under those first conditions, we get that guy. I don't know why I circled that like that, but it doesn't have to make sense, right? What's the product in the bottom situation with the bulky base? It's going to be our Hoffman elimination, which means we end up with the least substituted product. That last structure that's drawn there appropriately in that space is the correct product for that last one. Okay. We have the tertiary alkyl halide, and we have the bulky base. That's going to force the Hoffman elimination. We see the least substituted product pop out of that one. Okay. Oh, officially on that one, on that last one, yes. We should draw a wedge for the methyl group because we didn't change that one. Or actually for both of those. Shoot, my bad. We didn't change that stereochemistry, so we should specify it. A question or a way to ask this in a different fashion could be we run this elimination. Is the product optically active? If we went under the E1 conditions, is it optically active? For it to be optically active, what do we need? A chiral atom. Do we have a chiral atom in the E1 product? No. So is it optically active? No. If we run under the E2 conditions, do we end up with an optically active product? Yes. So if we aren't careful like I was initially and left the wedge off, we might initially say no, because we didn't add or we removed the detail that was given to us. Okay, so make sure you persist that information all the way through. Okay, in the interest of time, now I'm going to bump forward, which is exactly what I wrote underneath it. Within our E2 summary, our E2 summary gets a little bit more difficult. Our substrate is going to be dependent on what makes the stable pi bond. It's kind of interesting. Where have we seen that definition before? Pretty much the same thing as our E1. Very slightly different because we're looking at the most stable pi bond instead of the most stable carbocation, but they're very, very similar. So if I went through to predict the substrate structure, a tertiary structure will react faster under E2 conditions, then secondary, then primary, then our methyl. And our methyl can't do an elimination. Okay? And that's because our tertiary substrate is going to generate a more substituted double bond than our secondary substrate. Okay? We'd end up with the exact same rules for our substrate structure as for our E1. Our E1 is also going to have tertiary substrate, secondary substrate. Okay? Can we pick something out? What if you have a primary substrate and say a wicked strong base, say T-butoxide? What reaction are you going to get? Did I say secondary substrate? Primary substrate. Does the primary substrate run under E2 conditions?
No.
No. So that wicked strong base doesn't act as a base, it acts as a nucleophile. What's the product? SN2. So if you see a primary substrate, you've got a big red flag that the only mechanism that you would expect to run would be the substitution. Okay, when is that not the case? I tell you to do elimination with it. Okay? Which in theory we wouldn't ask because it's not going to happen to high extents. We still need a good leaving group. We still need a strong base. The solvent is going to be misleading because in almost all conditions it will be protic. Your regiochemistry, we will favor the trans product. So remember I said that our products, we only get one, but it's one per hydrogen. You'll notice in a lot of circumstances you'll have multiple beta hydrogens to eliminate. With each of those beta hydrogens you get one product. If one of those products is the trans and one of them is the equivalent cis, the trans is formed predominantly because trans is more stable. Okay? So we can see the cis pop up in a much larger extent, and a lot of that's just going to depend on the structure, so you have to watch out for that. The complications, we have to have that anti-alignment, and we do have the option for Hofmann eliminations as well. Okay? So we've got all of these little pieces, everything kind of falling together, and we have to make sure we keep them as separated as possible. Okay? One of the last things that we'll address as kind of new material within this chapter, they also talk about forming alkynes. So elimination reactions make what? Pi bonds, not alkenes. An alkene happens to have a pi bond, so one of the most common things we'll see is our eliminations making alkenes. But they can just as easily make alkynes because what makes an alkyne? Pi bonds, and ultimately 2 pi bonds. So to make an alkyne, how many leaving groups do I need? 2 to make each of those pi bonds. Okay? So in the first example that we've got of making an alkyne, you'll notice that we really only have one valid leaving group, or one that actually left to make the alkyne, and that's because we started with an alkene. So we only had to eliminate one. So we took our hydrogen off, hydrogen, kicked our bromine out. In the second one, you'll notice that we have two halides so that we can go through and eliminate both of those. One of the conditions that's going to be kind of important when we go through and do the alkyne is we're now actually breaking a rather difficult bond to break with the alkene. The alkene has a lot of electron density, so bringing a base with a lot of electron density near that alkene is going to get a lot of repulsion. So instead of using a standard base like hydroxide, we have to use a much stronger base, and we will usually use a lot more heat. The stronger base, sodium amide. So there's a fun question. Why is sodium amide a stronger base than sodium hydroxide? Got nitrogen, true. Kind of accept that. That is the difference.
Oh. Nitrogen wants to have bonds.
It's not going to have to do necessarily with bonds. What's our primary difference between oxygen and nitrogen?
Oxygen is.
It's not size, it's electronegativity. They're in the same row. Oxygen is more electronegative, which means what does it do with those electrons? It holds them. The nitrogen is much more basic because it's less electronegative. It's willing to give up those electrons a little bit easier than that oxygen is. Okay? So we can form alkynes from dihalides. There's some nomenclature that pops up with this. We end up with vicinal and geminal dihalides. Pretty sure I'm getting this right. You might have to check me on this. The top situation is your vicinal, and the bottom one is geminal. You'll typically see the vicinal dihalides because we can make those a lot easier than we can make the geminals. Okay? So you're seeing the same reaction dynamics in both those circumstances. Okay? We are just about done here. So I want to talk about some things real quickly. The last 5 or 6 slides in this initial slideshow has a bunch of just summary stuff, deciding between E1 and E2. Very similar to what you saw for the substrate. So it's trying to classify all of those individual pieces. There is a typo there. That one definitely can't happen. And the primary doesn't happen quite as frequently, so we can kind of cross that out. So if we're trying to decide between those two mechanisms, look at the conditions you have and try and go through and process. Once you decide which mechanism, then it's looking at those last 2 rows to determine what your product is going to look like. Okay? Deciding between substitution and elimination. You've got a sequence of kind of steps that I've elucidated for going through. Strength of your nucleophile / base is going to determine your order. If it's strong, what order? It's got to be a 2 type. If it's weak, 1 type. Deciding between nucleophile and bases. So you can look for that negative charge. If you've got the negative charge, decide, is it a nucleophile or is it a base? Okay. If it's a nucleophile, you're looking at substitution. If you're looking at a base, elimination. Remember, the difference between those is a very thin line. There's only a few species that can only act as one or the other. Okay, so under most circumstances, it probably doesn't make sense to try and evaluate the difference at that point. Once you've got the strength of your nucleophile, you can look at your bulky bases favoring your elimination. You can move to substrate structure. We already addressed one of those substrate structure issues. If you have a primary halide, there's only one mechanism that works, okay, or works well. It's the SN2. If you have secondary halides, your SOL, you got to find something else. Okay, because every single mechanism runs under a secondary halogen. Tertiary halides, you get a mixture of your SN1, your E1 always, and then your E2 can pop up. You won't see the SN2. Okay? And then your high temperatures favor elimination. Please say this. More summary, another formatting of it. Complications. Okay? Trying to summarize where you get those big issues. Please feel free to pack up. And then we push into the radicals. I will post a lecture on radicals. It is relatively short as far as slides. I will try and get through as much of it as I can in 30 minutes. So I'm going to try and keep that video as 30 minutes or less. The very, very last slide of the radicals. Come on, don't stop the presentation. Sorry, I don't want to end it. Here, reaction summaries. All of the reactions that you're responsible for the exam. You've got your alkane reactivity. We'll have, the alkenes is actually shortened a little bit for your reactivity. It's not these guys. You're just having this section. And then your alkyl halides, you're responsible for substitution and elimination. Okay, so that summary slide is in the radical section. Okay, sorry, I gotta stop.